Talk about free fall drop today. So we've been talking about the acceleration of objects that are moving from side to side. Now we're going to talk about vertical acceleration. Okay, so when we say free fall, we're specifically talking about objects that fall with no restrictions. So basically what that means is that we're going to take air out of the equation. Air complicates things significantly, so there's no air where everything we drop is going to be in physics land. Okay. And in physics land, when I drop something, the air doesn't affect it. So let's say that I've got this little doll here and I just let go of it. It falls. And we know some things about its falling. We know that it's going to speed up as it falls, right? And you know that from life. We call that acceleration due to gravity because it is caused by the force of gravity. So when I hold my little doll up, gravity is pulling down constantly on this doll. And because it's a constant pull, it's a constant acceleration. So she's going to get faster and faster every second. She's actually going to increase her speed by about 10 meters per second every second as long as she's close to the surface of the Earth. And we call that the acceleration due to gravity, or little g. So it's this number here. Meters per second squared, of course, that has been measured, okay, and it is constant, it's not changing. So as an object falls, it is continually speeding up. If you like rides that drop you, like the Superman ride at Six Flags, either if it terrifies you or you think it's fun, it's probably because you're going about 10 meters further, because you're going 10 meters per second faster every second than you did the second before. So you're speeding up significantly as you fall. Okay, something important to know is that because we've taken air out of the equation and the only thing affecting the object being the force of gravity, well, gravity affects all objects in the same manner in that it will accelerate them all at negative 9.8 meters per second squared, no matter what size or shape they are. Okay, so if you have a pencil and a piece of paper handy, just go ahead and try to hold them even and then drop them. And you could probably see in mine, and hopefully you're seeing in yours, that the pencil definitely hits first. Why does it do that? So it does that because air is a factor, right? It's the paper has a very large surface area compared to the pencil, so the air can push up much more on the paper on a larger surface and slow it down. Okay, if I were to take the air out, then both the paper and the pencil would fall at the same rate, because now the only thing affecting them is gravity. Gravity is the same across the Earth, basically, and so it's going to affect things in the same way. Okay, there's actually a video that we'll link to the notes as well. It's just a really short clip, but Neil Armstrong, when he went to the moon, actually dropped a hammer and a feather to see what would happen, see if our theoretical physics was correct. So the moon doesn't really have air to speak of, and so you can kind of see them drop at the same. The picture is really grainy though, so Mythbusters actually tried it. They get a vacuum, which means they've taken all the air out of the chamber. They drop a hammer and a feather at the same time, and you do see them hit at about the same moment. So we need to remember that G is the same for all objects near the surface of the Earth. It is negative 9.8 meters per second squared. Okay. We are going to be using the same basic equations that we have been using, with just one little difference. We're going to specify now that we're talking about vertical motion. And so we have VYF equals VYI plus AT. We have delta Y equals VYI T plus 1/2 AT squared. We have VYF squared equals VYI squared plus 2A delta Y. Okay, and then technically we do still have delta Y equals 1/2 VYI plus VYF times delta T. That last one you're almost never going to use though, because you would use that when you don't know what A is. And we do know what A is if you're near the surface of the Earth, right? So if you want to simplify a little bit and you want to ignore that equation, you can. That makes it a little bit easier for you. Just have 3. Okay, so these should look very familiar to you because they're exactly the same as the horizontal equations we've been using. The big difference is now that we're just saying it's a vertical. So VYF is vertical final velocity. Okay, VYI is initial vertical velocity. So if I drop something, it has a VYI at the top, which is 0 because I'm holding it still before I drop it. And then it's going to fall, and as it's hitting the ground, it has a VYF, or a final vertical velocity. Okay? And then the important thing to remember also is that A is always going to be negative 9.8 meters per second squared as long as the object is on the Earth. If you have a problem where the object's on a different planet, then it's going to, A will be something different. But the problem will either tell that to you or we'll ask you to solve for it. Okay? Let me write that in. So G is equal to A, if that helps. Let's see. The other variable that might be kind of new to you is this one, delta Y. So remember, delta X is a displacement horizontally. Delta Y is a displacement vertically. So it's just how far it fell or how high up the object began. Okay? Okay, so using those equations, we're going to solve problems in the same way that we have been. On this type of problem, if you find that you're having a hard time starting it, you might try drawing a picture. Sometimes a visual can help. So either a picture in your mind's eye or trying to draw it. So we have in example 1, an apple drops from a tree and hits the ground in 1.1 seconds. So here's our little tree, here's our apple, it's gonna fall. So time to the ground is 1.1 seconds. What is its velocity when it hits the ground? Okay, so we are looking for VYF, what's its final vertical velocity, for the first question here. And it kind of seems like we have a problem, right? We know that for all those equations, we need 3 numbers, and we have 1 in our list. So this is a little bit tricky. However, we're going to assume the apple tree is on the Earth, so we know A, right? A is negative 9.8 meters per second squared for anything falling near the surface of the Earth. And we also know that the apple was just sitting in the tree before it fell. So we know VYI is 0. It started from a point of rest. Nobody threw it down. Okay? So now we have 3 givens. We have our 1 unknown. The variable that is not in our list at all here is delta y, right? We don't have that, so we need to choose an equation that doesn't have delta y. So that means we can eliminate this one, and we can eliminate this one, and we have to use this one. So we can narrow it down to just one possible equation. Okay? So let's work that out. So we decided we were going to use VYF equals VYI plus A times T. So VYF is our question. VYI is 0. A is negative 9.8. And T was 1.1 seconds. So for solving, I'm just going to do 1.1 times negative 9.8, and I get a negative 10.78 meters per second. Okay, so before I move on, let's just think, does this answer make sense? Should it be negative? Yes, hopefully you're saying yes. The reason it's negative is that the apple is falling as it hits the ground. It's going down. Just remember, the negative is a directional term. Okay, and then it's falling for just slightly over a second, so it should be going faster, just a little bit faster than 9.8 meters per second as it hits. Okay, so that was question number 1. Question number 2 is how far did it fall? So how far did it fall is delta y. Okay. We're going to use the same givens we originally had. we're going to pretend like we don't know what VYF is. So if we choose an equation that doesn't have VYF, then that eliminates this one, and it eliminates this one, and we have to use that one. That's our only possible equation that doesn't have VYF in it. And again, the reason we're doing that, even though we just found VYF, is that if we don't know what if we got VYF wrong and then we use it to solve in the next one, it's going to mess us up, okay? Eventually, you will have to use what you solve for, but right now you don't, so try not to, okay? All right, so we chose this equation, delta y equals VYI t plus 1/2 a t squared. Delta y is unknown. VYI times t is just 0, right? So I'm just actually going to get rid of that. If you don't like to cross things out, you can certainly write 0 times 1.1. So 0, and then I have 1/2 times negative 9.8 meters per second squared times 1.1 seconds squared. Okay, in your calculator, I would suggest that you do 1.1 squared first, and then times negative 9.8, and then times 1/2 or 0.5, and I get an answer of negative 5.93 meters. I'm rounding that just a bit. Okay, so we want to check and think, does that make sense? Should it be negative? Yes. How far did it fall? Implies a downward direction, right? And then our distance makes sense as well. Okay, so there's our first example. Number 2, King Kong carries Fay Ray up the 321-meter tall Empire State Building. At the top of the skyscraper, Fay Ray's shoe falls from her foot. How fast will the shoe be moving when it hits the ground? Okay, so let's give ourselves a picture. So here's King Kong, and he's holding Fay Ray, and her shoe falls. And it tells us that the building is 321 meters tall. And that's all it tells us. And then it says, how fast will the shoe be moving when it hits the ground? So in other words, what is VYF? By the way, VYF will not be 0 because we're talking about as it hits the ground. So it has not come to a stop yet. It's moving basically as fast as it can possibly move at VYF. Okay, so let's label our givens. 321 is a height, right? So we're going to call that delta y. We're also going to make it negative because her shoe falls that far. Okay, the Empire State Building is on the Earth, so we know that A is negative 9.8 meters per second squared. And then we can assume the shoe was sitting on her foot before it fell off. And so that means it begins at rest and VYI is 0. Okay, so now I have my 3 givens. I have my 4th unknown. Which variable is missing here? I don't have a time. So which equation is the only equation that doesn't have time? Take a look at your list. And hopefully you're choosing the one that says VYF squared equals VYI squared plus 2a delta y. All other equations we have a time, so we don't want to use them because we don't know the time and we don't care about the time. We don't want to have extra variables in our math that makes it significantly harder. Okay, so VYF is our question, VYF squared. VYI was 0, so 0 squared is 0, plus 2 times negative 9.8 times negative 321 meters. And again, that's negative because the shoe is falling that far. So in my calculator, I'm going to say negative 321 times negative 9.8 times 2. And I get an answer of VYF squared equals 6,291.6. I don't want VYF squared though, I just want VYF. So what do I need to do to finish this out? I need to take the square root. Okay, so if I take the square root of that answer, I get a VYF of 79.3 meters per second. And then I evaluate, does it make sense? So her shoe should be going very, very fast off the Empire State Building so that the number makes sense. However, what am I missing? VYF, the shoe is falling down, so I need to add a negative. Okay, and then my answer is finished. So all velocities always need a direction. Don't forget about that part. One quick note, if you forget to put the negative here, it's not a huge deal, but you'll have negative 6,291. Your calculator will give you an error message if you try to take the square root of a negative number. So just take the negative off, do the square root, and then put it back on your answer. Okay? Okay, I would encourage you to pause the video and try this one on your own and see if you can get it. I'm going to go ahead and walk you through it. So we've got baby blue jay. Mama blue jay is dropping a worm in the baby chick's mouth. The worm misses and falls from the nest to the ground in 1.5 seconds. How high up is the nest? Okay, so here's our little worm. It's gonna fall. Hits the ground in 1.50 seconds. The worm was at rest in Mama bird's mouth before it fell. So VYI is 0. A is negative 9.8 meters per second squared. And the question is, how high up is the nest? So delta Y is our question. Okay, so the variable that we don't have in our list right now is final velocity. So if you take a look at your equations, the only equation that doesn't have final velocity in it is this one, VYIT plus 1/2 AT squared. Okay, so delta Y is our question. VYI is 0, so 0 times any time is 0, so I'm just going to cross that out. Say 1/2 times negative 9.8 times 1.5 squared. And again, I would suggest that you start at the back end with your calculator and do 1.5 squared first, and then times negative 9.8, and then times 0.5, and we get an answer of negative 11.0 meters. So now I go back and think through, does my answer make sense? How high up is the nest? So what we calculated was how far the worm fell, but that would be equal to how high up the nest was, right? But if the question is how high up, then I need to turn this into a positive. Okay, so mathematically, we came out with a negative answer, but that's why we always go back and look at our problem and see, did we actually answer what was asked? How high up is a positive number. Okay, and then last but not least, we have our giraffe. Again, pause this, see if you can do it without me. I'll walk you through in case you need it. So a giraffe who stands 6 meters tall bites a branch off a tree to chew on the leaves, and he lets the branch fall to the ground. How long does it take the branch to hit the ground? Okay, so we have a height, right? Giraffe is holding the branch at 6 meters up. It's going to fall that far, so I'm going to turn that into a negative number. We know that the giraffe is holding the branch in his mouth before he drops it, so VYI is 0. We know the giraffe is on the earth, so A is negative 9.8 meters per second squared. And the question is how long, and so that's a time question. I didn't draw the picture for this one, but again, if you find that you're really having a hard time with the numbers, draw yourself a picture and label it. It makes it much easier to figure out what to put where. Okay, so what's not in our list is final velocity, so we need to choose an equation that does not have final velocity in it. The only option is this one, delta y equals VYIT plus 1/2 AT squared. Okay, that's our only possibility with no VYF. So it kind of seems like we have a problem here because not only is t not isolated, we also have t and we have t squared, and those are not the same, right? But it's going to turn out that it doesn't matter because VYI is 0. So 0 times anything will be 0. So I'm just going to cross that out. And now I only have one variable that's missing. Okay? So let's fill them in. Negative 6 meters equals 1/2 times negative 9.8 times an unknown t squared. Okay, so first thing I'm going to do is 1/2 times negative 9.8, which is negative 4.9 meters per second squared times t squared. And then I'm going to divide both sides by negative 4.9 to get 4.9 to get t by itself. Okay, so I have 6 divided by 4.9, and that gives me an answer of t squared equals 1.224, lots and lots and lots of decimals, okay? But I don't want t squared, I want t. So my last step is to take the square root of that. And so I get an answer of 1.11 seconds. I'm going to do 3 sig figs because 6 has 3 sig figs in it. And I was dividing mostly in this problem or multiplying. And so there's my answer. Okay, so free fall problems, you have a set that is for just dropped. Couple of rules that you can know. All of them, VYI will be 0. All of them, A will be negative 9.8 unless the object is not in the earth. Okay, so it's going to look at first glance like they don't give you enough information, but they're givens that the problem assumes that you already know. Okay, reach out if you have questions.